Right. Hi, everyone. Welcome to the online causal inference seminar. So today we have a talk by Keele from University of Pennsylvania on so many choices, the comparative performance of statistical adjustment methods. Our discussant after the talk will be Díaz from Cornell University. So yeah, we look forward to these talks and getting into the details. Today, Ying will be handling questions. If you have questions, feel free to drop them in the Q&A. I'll switch over to Ying, who will explain in more details.
Yeah, so if you have questions, please submit the questions in the Q&A section. If you haven't used it before, it is at the bottom of the Zoom window. And please try to avoid sending the questions in the chat because the Q&A section will help us better track the questions. And that's it. I'll give the stage to Luke.
Okay, thank you everyone for this opportunity today.
Yeah, feel free to start sharing whenever.
There we are.
Yeah, great.
Okay, so today I'm going to give more of an apply, but definitely a more applied talk, not some of my new breaking ground methods, but sort of an overview and a little bit of a reflection on what I've learned over the last 3 years. 3 years ago, I switched jobs and took a job where I interact with clinical investigators a lot on a regular basis. And it's been good to sort of see, well, it's one of those things a little like sausage. It's kind of scary to see up close how it's made. But I've learned a little bit about the gap between what happens at places like the American Causal Inference Seminar and what happens on the ground, and some of the communication I think we might need to do to make applied work better. However, before I get into the talk, I'd like to give a quick plug for the Society for Causal Inference. Membership is live. There is a link here where you can go and join the Society for Causal Inference. We are about to hold elections on March 1st for the first permanent set of leadership positions. We have a great slate of candidates running from all over the country. However, to vote, you have to be a member. And then, as you may know, the early bird registration rate for ACIC ended on Friday. However, if you are a member of SCI, you still get that. So if you missed that and would still like the discount, that is still possible if you're a member of SCI. SCI is meant to be the home of the American Causal Inference Conference. And as once the leadership gets into position, we have lots of great ideas in terms of new initiatives in causal inference. If you'd like to be involved, please join. So today I want to talk a bit about essentially adjusting for confounding and observed confounders. There's probably the most common study design, not just in biomedical clinical applications, but across the social and medical sciences, is simply to assume, right, that there are no unobserved confounders. Roughly, I'm being here, and then adjust for those confounders via a statistical model. I would say in many of those applications, that implication is not fully understood, but there's definitely a move to where we're looking at some sort of implied, if not explicit, causal effect, and we have a series of confounders that get controlled for. That is, I think you can, I'll let anyone disagree that is a very, very widely used study design, particularly in clinical studies of various sorts. In terms of regression, in terms of how we adjust for those, right? Once we move to point 2, there's going to be some sort of adjusting for confounding. There's going to be controlling. People talk about controlling for the number of phrases that get used, right? But we essentially move into a multivariate world, right? It's still common even in clinical studies to do a bunch of bivariate regressions and then run a multivariate regression. As soon as you move into that regression world, right, we're talking about some sort of adjustment method. And it wasn't that long ago that regression was the only choice. Then essentially, I would say matching and general propensity score methods have sort of gained quite a bit of popularity over the last 20 years. Though it's always been interesting to me, the gap between the introduction of the propensity score, and then if you look at the citations for the original propensity score paper, it's basically almost totally uncited until around 1999. And every year since 1999, there's this huge increase in trajectory. So I kind of like to think around 2000 is when these methods sort of start to get more popular mainstream currency. And right now there are many, many different methods, right? I'm going to give you a little sense, right? There's still people debate a little. I still get questions about, is it okay to use least squares versus a logistic regression? But matching itself, there's subclassification, standard propensity score matching, kernel matching, optimal matching, genetic, right? I don't think I didn't capture the full list of, I'm sure, proposed matching algorithms out there, but there are a number of those and there's debates, right? Each paper tends to show that it's slightly better than some other form of matching. Lately, I would say the big explosion in methods is a lot of increase in terms of weighting, right? For a long time, it was pretty standard IP weighting, but there's been a huge explosion in what I would call balancing weight methods, approximate balancing weight methods, stable balancing weights, CVS weights, entropy weights, overlap weights. There's a lot of different sort of weighting methods. And then, right, for a long time, there were two. BART and Twang have actually been around for quite a while, but there's been a bunch of superlearner TLME, GRMF. There's a huge increase, right, in various forms of what I'll call machine learning based methods, which tend to be importing a series of adjustment methods that are used for prediction of various types. So you can see already here, this is not anywhere meant to be an exhaustive list, but it's a fairly relatively large list of certain options that one could choose in terms of adjusting for observed confounders. There is a widespread confusion, I would say, out there. This is an anecdote from a paper I was a co-author on, or later co-author on. A clinician I know at the Children's Hospital of Pennsylvania had worked with Dylan Small and Paul Rosenbaum and implemented a fairly sophisticated form of optimal matching for a paper at JAMA. The statistical editor at JAMA came back and said, we don't understand this. Can you please redo this as a simple propensity score match? Right, which is not, I can imagine other forms of adjustment you might adjust, but that didn't struck me as an odd step back. If you look through the clinical literature, particularly when there's a survival outcome, regression is still essentially dominant. Cox regressions are still, I would say, and logistic regressions by far and away the most standard methods used. And causal inference methods are surprisingly much of what we think, and I think this is when you spend time at somewhere like the IC, you think IP weighting is standard. I was involved in an interview process 2 weeks ago where we were interviewing people with MAs in stats or biostatistics, and not a single of the three candidates had heard of IP weighting, right? So a lot of these things we take for as given as more robust, different types of methods. There's still like widespread confusion in terms of sort of what is better, what is optimal, what should you be using, and should we ever abandon regression? And by regression, I mean something with a pretty vanilla, linear, additive functional form. However, I think one of the things that has struck me as I've gone back through the literature, because this is in causal inference, you might argue this is one of the larger literatures that is developing new methods for statistical adjustment. That is, in terms of effort, there's, as I said, many, many papers on this topic. Why so much effort? And one thing that has struck me is it's actually sort of within much of the causal inference literature implied as to why we need to focus on more flexible methods of statistical adjustment. That is, it's very rarely communicated what model misspecification is. Right, if you can, one way, this is from another paper, a paper I wrote with Dylan and Xingyao, and you can sort of think about what actually is going into any particular causal effect. Is there's possible hidden bias, which in this sort of setting would be bias as a function of omitted confounders. In these studies, where essentially we've assumed that is zero and taken that as given. There is misspecification bias that is due to incorrect functional form in the form of statistical adjustment in this setting. And then there's statistical noise. And I don't know that there's often much communication about like the magnitude of how big this particular bias, this misspecification bias can be. There's also, to me, I think a little bit of a tragedy in that we never quite know in this setting where we're in this thing where the hidden bias is zero. We do know it in some settings, but if you are in this world where the no unobserved confounding assumption holds and you bias your specification, your result is a function of specification bias, which isn't generally entirely preventable. That's a bit of a tragedy. in my view, in terms of estimating causal effects. Right? That is, the model specification typically arises due to incorrect modeling of choices, nonlinearity in various forms, hidden interactions are probably the two main sources of it. I came across, I've developed a couple little simulation exercises. I think that is helpful to communicate to people how large the magnitude of what this bias can be. In this simulation, it's a very simple setup. We have an outcome, we have Z, which is a treatment. There's a single continuous control variable that has a quadratic functional form. The magnitude of the bias, I don't get into it here, it's in the paper, depends very much on how much correlated X is and then the variances across these two terms. But we can think of three scenarios. One, you can omit X, right? We're omitting a confounder. X is designed in this simulation to be a confounder. It has to be in the equation. You can model it as linear, right? We can induce model misspecification on purpose, or we can include X in the model with the true quadratic specification. And I think this is, I think, when I show this to more applied researchers, I think this starts to get a little more attention, right? If we get the functional form right, this is each of these histograms is the distribution of the estimates over 1,000 simulations. When everything is right, when things are correctly specified, we are hitting the true effect. When we omit the confounder, right, we are clearly shifted away. The distribution is no longer overlaps with the true distribution. But model misspecification itself, depending on how you configure the variance and covariance between Z and X, can induce specification that rivals or is greater than that of omitted variable bias, right? And it's really this when we think about when we worry about flexible forms, right? It's we're trying to prevent this form of bias. In terms of reducing model specification, right? For a long time, I think the main emphasis has been on what I would call a semi-parametric nuisance parameter approach. And this is how I would group essentially both matching and in most forms of weighting, where the functional form specification for the control variables, the confounders, is left left unspecified to some extent. There's various levels to how flexible the people are in that area. Again, it depends on how the propensity scores are estimated. There's a lot of different ways you can relax it, but this is sort of, because as propensity score methods have become dominant, this has sort of become probably the most common way that people try to reduce model misspecification. And then there's a variety of different forms of non-parametric estimation methods, again, often associated with what we the term machine learning, which have also been employed to increasing effect, right? So let's run through sort of how the sort of combinations we can sort of think of in terms of how these different methods can be combined in terms of the degrees of freedom that it gives people, researchers, in terms of estimating causal effects. So here in terms of the notation, Y is going to be an outcome, X is treatment, and Z is treatment, and X is a baseline confounders. So when we talk with clinicians, this is a choice that people implicitly or sometimes explicitly make, right? That is, sometimes the approach is outcome focused. Most regression, any sort of regression setup, of course, is going to be outcome focused. Again, most of the semi-parametric nuisance function approaches are going to be treatment focused, right? These are propensity score methods are, of course, treatment focused. And then, right, and gaining currency over the last 10 years or so, of course, is some, by doubly robust, some combination of these two. Again, the combination sometimes is simply running matching and then running regression with some additional adjustment on top of that, or it's much more explicit in terms of the propensity score weighting methods that incorporate these together. And then in terms of our estimation methods, right, there's a lot of plug and play, of course, across these two methods in terms of whether you use regression, the propensity score methods, in terms of what's happened, in terms of what choices people make. There's been a lot of work on what I would call advanced weighting and matching methods. These are all, again, more computationally flexible things that, unlike propensity score methods, are directly targeting balance. I think that's a key shift. Both matching and weighting have moved away from just estimating a single dimensional propensity score and targeting the objective function in terms of balance directly. And then I think, of course, in the last 5 to 10 years, most of the focus has been on machine learning methods. And then, of course, in terms of what you see in terms of in the applied literature, there's not much use of beyond the first two, but there are any number of combinations. There's work on using regression models with a propensity score on the right-hand side. The most common is some sort of IPW weighting and matching with some sort of outcome regression on top of that with perhaps some additional bias correction. But there's other things. People use a GBM for propensity score estimation to write. So there's a lot of different sort of combinations here. I think in terms of if we think about what should be generating some applied, right, when you start to look at all these lists, and if I talk to applied collaborators, if I show them this long list, right, clinical collaborators, clinical researchers are very busy people. They tend to be MDs with full practices that are then doing research in addition to that. It's always struck me as I work with more medical researchers, their incentives, right, or at least at Penn, a lot of clinical researchers get penalized if they do too much research, because then they stop bringing in clinical dollars. So they're very busy people. If you show them a long list of methods, they're like, I don't know, I don't have time. Let's figure it out. Let's run a Cox model and move on. So in terms of generating some sort of advice, I think some sort of questions that I think that would be relevant to a more applied literature is should we always use doubly robust methods? At least insofar as should you always do both a treatment-focused and an outcome-focused approach and compare the results? That's not strictly speaking a doubly robust approach, but it's at least understanding the fact that the model misspecification can happen in across those two different approaches. Should we move toward ML-focused, machine learning methods-focused approach at all? There's a relatively recent discussion on this in statistical science in terms of discussing the data competition out of ACIC. That's clearly an undercurrent there. Should we just let the machines always sort this out? Should that be our recommendation to our applied researchers? And should we, in particular, I think, should we push towards in my mind, I'm going to talk a bit about this. The theoretical literature really seems to be converging on a particular form of a doubly robust and machine learning approach only. That is, in particular, I don't think there's any doubt that machine learning methods are going to be your most flexible choice in terms of avoiding functional form misspecification. However, I was reading a review by Victor Chernozukov and some other people. It's pretty clear ML methods on their own have pretty poor inferential properties right across. They weren't really designed for inference. There's been a lot of work the last 5 years, and there's no real name for this. This is the name that Edward Kennedy and I came up, called the doubly robust machine learning framework. That has clearly showed us how to combine ML methods, but get the right form of optimal efficiency. That is, in this setup, there's always a doubly robust framework. There's a series of bias-corrected estimators using influence functions. And then, of course, the estimation is combined with the correct form of sample splitting for the selection of key tuning parameters. To me, this framework clearly has the best theoretical properties. From my reading of the literature, people can debate. I'm open to debate about that. But right, is it necessary? Right, is the marginal gain from this framework enough in applied settings that this is what we should be pushing any sort of applied collaboration toward? So this talk covers a couple of different papers where I'm sort of interested in sort of interrogating these questions. And I'd like to do it essentially in terms of evaluating performance. There are two main ways that we do that. And that's either recovering experimental benchmarks or simulations, right? The ACIC data competition is very focused on simulations. And our response, I think, I'm in that exchange in statistical science. And I think there's pluses and minuses to both settings. In this case, I'm going to focus on two experimental case studies. We're going to look at some two places where we have experimental benchmarks, but observational data, one of which has not been widely used, neither one of which is the Lalonde framework. So what I want to do is leverage these two different experimental benchmarks with some focus on these questions to give us some idea, right, of answers to these two questions. I've been encouraged to pause for questions, and I want to take this point at my first sort of pausing point in terms of taking questions.
There are no questions in the Q&A section, but we encourage people to raise questions. And I think we can continue.
Okay.
Actually, look, there's just one
Oh,
question that showed up right now.
sure.
How do common support violations fit into this framework? That's a question.
So again, that very much depends on which method you're talking about. In the weighting setup, like overlap weights are definitely designed to particularly target overlap in particular. Most matching methods, again, within matching, propensity score matching itself has got there's some rudimentary diagnostics that you can think about overlap. But there are optimal subsetting methods that are essentially matching methods designed to trim for common support. Machine learning methods, some of them, again, have a BART, right, has trimming rules to enforce common support. So that's just another degree of freedom in terms of across these different forms of methods. Yet another form of degree of freedom in terms of how we choose these adjustment methods. In the clinical literature, I don't know that that topic is too well understood. In this literature in general, there's some methods are designed to target particular poor overlap, and others are less designed to do that. And it depends on sort of which of these combinations. Sometimes the methods are chosen for that reason. That's one reason people will sometimes match and then run regression on top of it, right? That's a recommendation out there, right? The matching is designed to sort of enforce the common support so that when you run the regression on top of it, you're avoiding extrapolation in that particular way. So it kind of depends on which combination is selected and whether you think if you think that's an issue, you can select among these different methods for that to enforce common support.
Great, thanks. Can we just do one short one also? Do the Bayesian approaches count to the ML category?
Oh, that's a good question. I mean, BART, yes. But I would argue, I'm probably going to offend some Bayesian when I say this. I think you could very easily construct a Bayesian setup that's not machine learning, right? I mean, if I could set up a logistic regression with some sort of prior on it and estimate a propensity score that way, and I don't know, to me, that wouldn't be a machine learning approach. What classifies as machine learning? I mean, I know Bayes when I see it. What classifies, right? A GAM is, you could argue that a GAM is a machine learning method. It's in Hasty and Tibishirani, right? But it's a pretty vanilla. No, I would say in general, BART's, yes, Bayesian can be machine learning, but it doesn't have, I would say it doesn't have to be. There will probably some who may disagree with that categorization, but that's sort of my take on that.
Great, thanks.
Sure.
Yeah, go ahead.
So I want to talk about the first case study. This is a case study that's one I came across with a collaborator in the UK. It's a really cool study. I wish we did this a bit more often. So the clinical question, they had a clinical question. GORD stands for gastrointestinal reflux disease, essentially very bad heartburn. For people with advanced severe GORD, there are essentially the main form of treatment is something called a proton pump inhibitor, which is essentially a form of medical management treatment. But there are also forms of surgical treatment for GORD. The trial in particular, that is the main applied research question of interest, was whether surgery was superior to medical management. Medical management has some long-term, because you're taking these medications for a long time, there can be long-term side effects, where surgery is meant to be a one-off intervention that avoids some of those long-term consequences. So that was the two arms, essentially, the study are medical management versus surgery. But what was really nice about it is reflux was the title of it. That actually stands for something that I forget. Often these large studies have acronym names. But what they did is they actually did a parallel RCT and observational study. So what actually happened here is they had their baseline enrollment criteria, and the enrollment criteria had to do things with age, but mostly it had to do with you needed a GORD a diagnosis. It had to be a certain level of severity, a number of sort of standard clinical characteristics that were used to be enrolled in the study. Once the patients were enrolled in the study, they were given a choice. They were given a choice of, would you like to be in a randomized trial arm, or would you prefer to be in this patient preference arm? And what happened in there, that was entirely up to the patients to choose between the two arms. If patients selected the RCT arm, they were randomized, right, as would be the case in any clinical trial. They were randomized across the two arms. In the patient preference arm, they, in consultation with their doctor, were able to select which form of treatment they were given, surgery or medical management. To give you an idea of the overall sample sizes here, so 810 patients made it through the enrollment criteria, who were enrolled in reflux. 357 opted into the RCT arm, and then 453 opted into the patient preference arm. Across surgery and medical management, it's 178 received surgery and 179 received medical management. In the other arm, it was a bit more imbalanced. 261 opted to take surgery, and then 192 opted for medical management. So we have the full data set. We have a set of baseline, the set of baseline covariates were gathered here from the enrollment criteria. So in terms of work on, like this, work on using the target trial framework, this is all very nicely set up here, and that the design takes care of all that, and the enrollment criteria and the setups were essentially designed to be parallel across the two studies. And this was conducted in the UK at 21 different medical centers across the UK. So the main two different outcomes here are health status. EQ5D is a questionnaire that's used more widely in Europe. It's a health status questionnaire asking people about their health status, and then they have quality of life. Both of these are a series of survey instruments that are then turned into a scale via principal components. So our outcomes here are both these principal component scaled outcomes that are roughly essentially continuous. So those are the two main outcomes. And here they actually looked at over a few different periods, but 3 months was the first measure of the first time that they measured it after the intervention. So what's nice here, because we have the data from both the trial or the full data set from the trial and the observational study, right? We can estimate the treatment effect in the RCT. We can also then estimate it in the non-randomized arm. And then you can compare. In education, they like to use this measure where you take the standard deviation in the control arm and you standardize that. So it's a form of essentially a standardized measure of bias across the two arms. So you can essentially measure the discrepancy from the observational study to the RCT arm. So in this, this is an earlier paper. I was particularly interested after I'm going to cover. We used a lot of different methods in terms of estimating the observational study arm. So what we're going to do is we're going to vary how we estimate the observational study estimates. One thing I noticed in the results from the ACIC competition is that a number of the methods that performed rather poorly were these series of Stata commands that Stata actually has a whole suite of, they're called TE effects commands. They're essentially designed to implement causal inference estimators more easily for you. I noticed that those often performed rather poorly. So one thing we did in this first study is we varied not only the methods, that is, we used matching and regression and those sorts of things, but we also did some variation across. I used the full set of Stata commands, but also coded several of these up in R myself to sort of get some sense of what's going on in terms of the software. That strikes me as important in the sense that the Stata commands are often some of the most widely used, I think, in applied literature, and that they're easily accessible and don't require any sort of programming. So to give you, here's a list of everything we tried. So we have, in terms of outcome model focus, Stata, we did regression adjustment in Stata. However, I should say This is not using the reg command in Stata. This is using the TEF. So the TEFX has an RA option, which does regression adjustment. In R, I just did regular regression adjustment. There are some interesting contrasts sometimes across these two commands. And then I chose selected BART as a machine learning, but outcome focused setup. In terms of the treatment focused across Stata, so Stata has essentially, the TEFX has two different options for IPW and stabilized augmented IPW weights. And then it has a PS and a nearest neighbor match command. So it has essentially two forms of matching. At least at this time of writing, Stata comes out with updates very often now, and there may be other options in there now, but these were the options available in Stata as of about 3 years ago. And then in R, I just coded these myself. For the propensity score match, I used just standard matching there. The covariate matching is essentially using a Mahalanobis distance. And then the more sophisticated form of matching, I use something called cardinality matching, which is a method of matching, integer-based matching developed by Jose Zubizarreta, that I think is like more advanced forms of matching, is designed to directly target covariate balance in terms of the optimization. It also can trim for overlap as well. In terms of outcome versus treatment, that is, we think of these as doubly robust. Most of these, the Stata has options to add regression adjustment onto some of these commands. Then I just added regression adjustment to these other two. The doubly robust is just using an augmented propensity score weights. And then in terms of more sophisticated methods, I use the generalized random forest methods. This is the method of Athie and Wagner. And then in terms of a superlearner with a TLME, this is, I used the MP Causal package from Edward Kennedy that ties into the superlearner package in R. And I did the estimates that way. I'll talk a little bit about the learners that were included this in a moment. So we've got, essentially, as I said, we have two outcomes. We've got these different sets of outcomes. I'm going to stratify the results in 3 different ways. I'm first going to compare the machine learning based methods, and then I'll contrast the Stata and the R non-machine learning methods. Across these sometimes are a little bit small. So this upper row here is the generalized random forest. This vertical line here is again all across the x-axis across all of these is the metric is standardized bias. So this is essentially the distance between the observational study estimate and the RCT estimate with a confidence interval. As points get close to the vertical line, the observational study method is doing better in terms of recovering that experimental benchmark. So this top row here, these are the two outcomes. GRF does fine, same with BART. What was very interesting here, and this is going to be a thing I'm going to come back to, in the initial superlearner here, I included a random forest, a lasso, and a GBM. I alternated when this result came back. I actually spent some time swapping learners in and out, and it never actually moved closer to this. I never could quite understand why but that's going to be, well, I'm going to come back to that. This sort of setup here across the TLME superlearner framework, in these applications seem to be somewhat sensitive sometimes to the inclusion of the learner. In terms of Stata results, so across the top here, we have the TEFX command doing regression adjustment, standard IPW stabilized weights. Then this is IPW with the regression adjustment, PS match, NN match. And then only the NN match command allows you to do the regression adjustment on the outcome model after you've matched. Here, quite noticeably, both the two matching commands are actually the worst performers actually across all the methods we tried. They end up being, here, notice the standardized bias is actually half a standard deviation. That's actually rather large. It's over a quarter of a standard deviation here. And it was, interestingly enough, for reasons I don't fully understand, because I'll explain later, when you add in the regression adjustment, so remember the regression adjustment here is being added to this nearest neighbor match command here, and it actually moves it in the wrong direction in a very large with considerable amounts of bias. So in both these settings, these stata commands, which are probably, from my understanding, NN match and PS match, are probably some of the most commonly used methods across everything I'm going to show you today, end up having not only just very poor performance in general. And here again, notice here the regression adjustment is actually this regression adjustment is being added to this estimate, and again, it's just zero movement at all. Mistakes can be made. So in R, the results are a bit more. What's interesting, as notice here, right? These basic propensity score matches are not doing very well. Here, standard IPW does fine in all S settings. The only thing I think the behavior here is a bit more normal in both the propensity score match and the Mahal-Novus match. If you look at based on the initial settings, the balance is not great. Cardinality matching, on the other hand, balances quite well initially, and the results, there's very little bias. However, in both these instances, once we add in the additional bias reduction from an outcome model, we have no problem. Which is, I find it's very hard to understand exactly what the stata commands are doing. Like a lot of things that are not open source, it's hard to understand. So it's surprising to me here that the additional regression adjustment here in stata is failing, where in R it's doing exactly as we would expect in terms of taking the imbalances left in the match and removing it to an outcome model. For this other outcome here, only the propensity score match has is biased. But again, once we add in regression adjustment on top of that, the bias is very small, well under 0.5 of a standard deviation. So if we look, and to me, it was quite interesting that here the mode of software versus something we don't really tend to think about actually has pretty key effects on the results. That is, both the PS match and NN match are one of the only two that failed. Again, however, both propensity score matching and even in R performs poorly until you add in the regression adjustment. Clearly, that should be caught by any reasonable analyst, in the sense that both of these displayed imbalances that were then you would either want to adjust your match or again include the outcome adjustment. But it's here. And then the other thing that I thought was interesting again is that it is the case that one of the more advanced machine learning methods did struggle with one of the outcomes in particular. So let me quickly take this as a second point in terms of questions.
Yeah, we have quite a few questions, but there are some common ones.
Okay.
The first is a question raised by 3 people, which is about the characteristics between the two groups, like the randomized study and the non-randomized study. Like, did you account for the difference in these two populations?
So because there are some differences across the two, so there are very few differences across the randomized. If you look at in the main paper, we actually present balanced statistics across this. We actually present the balanced statistics across the two arms, and then within the RCT arm, of course, they're going to be balanced by design. But because the enrollment criteria are standardized across the two, there is some selection bias there is some modest degrees of selection bias in terms of observed covariates between the observational study arm and the RCT arm, but it's not dramatic. But in terms of doing the statistical adjustment itself, no, we didn't correct for those. And the reason we didn't is that's generally, like if you look at the way these studies are typically done, it was interesting on Archive today, Eric Chechen and some other researchers actually have just put up a new preprint on ways to design observational studies from experiments that takes this a little more into account. Most of the original, like Lalonde studies, don't do control across the two arms. We're just trying to see how well, based on the observable characteristics within each arm, can I recover that experimental benchmark.
Thanks. We'll deal with another question, which is mainly about the paper and data by two people. Like they're asking whether the paper or the data set are available.
The paper is available, the data set, you'd have to apply the original investigators to get the data set. I could talk to, if you talk to me, I can put you in touch with the right people. The paper, at the end of the thing, I will put, I have a citation for this paper. At the end of the talk, I have a citation for this paper.
Thanks. Yeah, well, we still have a few questions left, but I think for the sake of time, maybe we just continue.
Okay. Yeah, and I don't have too much more to go. So in the second application, this is about right heart catheterization and whether it reduces mortality. So across observational studies, the general argument is that it does. In the RCT, or well, I paraphrase that. In the observational studies, we find that the RHC seems to be attributed to higher mortality. In the there's a couple of RCTs done in the UK, and there they find no relationship between RCT, the right heart catheterization, and mortality at all. It doesn't appear to reduce mortality. So here I'm using the Connors data. This data set is widely available. You can download the raw data set from Vanderbilt, but this data set has been published many, many times. It's a nice example. There are a lot of continuous covariates. A lot of the confounders are continuous because they actually have bedside physiology data, and the overlap is quite poor. Here I don't have access to the RCT. Those are just published RCTs, but I haven't been able to get a hold of the actual RCT data itself. So here we're essentially, the goal is to see whether the observational study methods, how close they are to essentially covering zero, which is the basic finding in the RCTs. Here I'm using a much more limited number of methods. I'm going to focus on regression and IPW. That is a fairly standard form of outcome modeling and a fairly standard form of treatment modeling. Then I'm going to do two different, more advanced flavors. I'm going to do optimal matching with fine covariant balancing. This is something a colleague and collaborator, Sam Pimentel at Berkeley, a method of matching that he came up with is, again, designed to target particular balance considerations. And then overlaps is developed by Fan Lee, her group at Duke. These are a form of weights that are designed to target overlap in particular, which is both seem relevant here, given that when you look at the raw data, there's clearly overlap issues. And then in terms of more advanced DRML methods, I used both GRF and a superlearner TLME combination. So here, if you look at, so this is just a regression model with some with limited interactions and nonlinearity included. So the IP weighting here is, again, simply done with a logistic regression in terms of estimating that propensity score. Both of these are proportions. This is the difference in risk, is a risk difference. So this is saying that if you got right heart catheterization, you were 6.3% more likely to die. And the IP weight, right, both of these, even though one's outcome focused and one is treatment focused, right, the results are essentially identical. So for the match, I worked pretty hard on this match to get it balanced. As I said, the overlap is quite poor. In the RHC, in the original data set, there are 2,184 patients that got RHC, and there are 3,551 controls. To balance that, if you look at the balance going into the data, it's quite poor. There's standardized differences of above 0.5. To balance it well, to get all those standardized differences under 0.1, I trimmed about, there were 1,547 matched pairs, so I had to do a pretty substantial trimming. So we lose about 600 treated observations to get this balanced well. There are a number of discrete covariates that I use fine balance to nearly exactly balance as well. What's interesting here again is the regression adjustment. Again, the amount of bias correction here from the regression adjustment is actually rather minimal. It moves it, but again, both of these have actually, in some sense, the commons is overlap, so I'm not going to make strong claims here. But these are both actually somewhat worse than a slightly more naive methods. So then I tried the overlap weights. Again, they're giving me both overlap weights with and then with regression. Again, I get very similar results to the naive methods. So then as I moved on, I noticed actually, this wasn't initially my plan, but the overlap weight, the package in R that contains overlap weights allows for a GBM. You can estimate the propensity score via GBM instead of a logistic regression. And I added that option as sort of a machine learning method, not a doubly robust machine learning method. And then the random forest itself are the first two that sort of clearly moved in the direction of the zero that we would expect from the randomized trial. Again, as I mentioned earlier, there's some sensitivity to the number of learners in the SL setup, the superlearner setup. So I started out with GLM, random forest, GAM, lasso, and GBM. And I get clearly some movement in the right direction. It surprised me, however, that there was this difference here with the GBM in there. It should seem to be a bit closer. Clearly, in the superlearner, this last superlearner here, I dropped the lasso and the GAM, and then here I only use the GBM. So it's interesting to me that in terms of if we think the GBM here, I think it's picking up. I've got some initial analysis plan. I think it's picking up on some hidden interactions, the random forest and the GBM. That seems to be the key driver of the bias here. It's interesting to me in terms of the averaging across the learners that doesn't really come through. That aspect of it doesn't come through unless I use a GBM alone. So, and to wrap up, I've been talking too long. Basic propensity score methods in Stata don't work well. I think it's pretty clear that at least you need to be doubly robust, at least in terms of estimating both, if not formally doubly robust, estimate both an outcome and a treatment-focused method and compare and make sure those agree. Across multi-simulations, the DRML methods rarely perform poorly. They're not a silver bullet. We did see some instances where they displayed some level of bias. GRF, I think, clearly showed the best results across all the case studies. I do think, however, I think it's something for in terms of investigation, how we communicate this to a wider applied audience. How do we make these tools more available? I'm not a great programmer, but I'm clearly more advanced than most of my clinical colleagues. And sometimes implementing the DRML methods, even in R, is not the most straightforward. It took me a while. I'm good at it now, but I learned I have to strip all the variable names off, or the data matrix often gives me errors. I think we have a long way to go in terms of communicating and generating these sort of tools for applied users.
Great.
Oh, and then here's that paper people were talking about. This is the paper that the reflux is from. And then the second application is a working paper that I don't have. It's not quite done yet.
Perfect. Thanks, Luke. There's many questions in the Q&A, as you will see. I think maybe if you could give like a short answer to one and then move on to the discussion so we have time. And feel free to review and see like which questions perhaps you find more interesting to answer after the discussion. Okay, so from Paul Ferraro, given all of the replicability crisis issues that have been raised over the last decade, why would using an experimental benchmark be superior to using simulation benchmark?
I guess I wouldn't. I don't want to get too much into the weeds. I got a paper that talks a bit about the contrast between experimental benchmarks and simulations. I guess my quick answer to that would be, is there pluses and minuses to both experimental benchmarks and simulations? I would argue that a lot of the replicability crisis is not coming out of the RCT literature. It's mostly coming out of other, it was in psychology, but there were a bunch of things that they were doing in psychology that I would argue don't happen in a lot of well-run RCT trials in clinical studies. We can debate whether that's the case or not, but the regulatory framework for RCTs is, I think, very robust, and the people who run those actually do a really good job. I think it's pretty different than some of the other forms of replicability problems, I would say, don't come from that RCT literature. We can disagree on that, but that's would be my.
Cool. Great. So Wonderful. Then let's move on to the discussion. Ivan, please feel free to start sharing your screen. And yeah, Luke, I totally invite you to review the long list of questions. It's been a very successful talk, I think.
Thanks.
Thank you, Iván. Thank you, Luke, for a very interesting and thought-provoking talk. I mean, the goal of giving practitioners a bit of advice in terms of what methods they should be using, I think is very important, and this provides a good solution and good insights into that. That said, I'm going to be talking a little bit more about a few of the more theoretical aspects of this issue. So I'll use similar notation to what Luke used. I'll start talking about a causal parameter that we want to estimate. Let's say the counterfactual expectation of y1, or sorry, the expectation of the counterfactual y1. What would have been observed in a world where everyone is treated, a target statistical parameter, which we can say for now it's the computation formula, for example, an estimator tau hat, which is usually just a function of your observed data, just the whole data set that we have on covariates, exposures, and outcome, and a probability limit for that estimator as the sample size grows. So actually, Luke showed us a decomposition like this. This is sort of me rephrasing what he had already said. If you want to know what's the difference between your estimator and the causal target, so you sort of have to take care of three quantities, right? The first one is statistical uncertainty, which tells you how far you are from the limit, just randomness in the sampling. Model misspecification bias, which is even if you take that limit, is that close to your target statistical parameter? And then we have identification bias as well, which is have we included the right covariates in order to get the causal parameter. And so the first point I want to make is that, of course, Luke said this. This talk does not focus on identification bias. To address that, we have sensitivity analysis, we have partial identification, we have other kind of tools. But I want to make the point that the choice of estimator not only impacts the misspecification bias, but it also impacts the statistical uncertainty. For example, we have different estimators have different properties in terms of convergence rates, right? Like how fast do they go to that limit? Do they converge at root rate? Are they efficient, right? So all of these estimators also have different properties in terms of statistical uncertainty. Okay, so that was sort of the first point. The second point is I mean, and Luke also mentioned this. There is at least three, or of course, at least three, but these are probably the most commonly used methods or ideas for estimator selection. The first sort of approach is to study their statistical properties, and these studies are usually done in large samples, like just asymptotic properties of the estimators, just because to do it in finite samples it's a little harder. There is numerical simulation studies, which are usually based on synthetic data, and there is benchmark studies, right? So we saw two examples of this kind of a benchmark study today. But one sort of point that I think is important to highlight is that benchmark studies and simulation studies are quite limited in terms of providing general estimator selection techniques. They just give you a one-off snapshot that only applies to that one data generating mechanism or that one data set. And so as a general estimator selection tool, they might be limited, but they do provide useful information. For example, they tell you when things break, and Luke showed us precisely what, how that happened with many of the data commands, right? But they don't show you really when things work, right? So that's a first problem. I do find simulation studies especially very useful for confirmatory purposes. For example, if you know that your estimator has to be efficient, that it has to be asymptotically linear, then you can use a simulation study to show those sort of asymptotic properties. And in particular, in the reflux study, which Luke discussed, the point that I want to make here is that the difference between the RCT and observational estimates actually conflate misspecification bias and identification bias, right? So on the one hand, we can take this difference and decompose it in this sort of way, which is similar to what I showed in one of the previous slides, we have statistical uncertainty in the RCT. Where, in the RCT, we don't have any sort of identification bias or misspecification bias. We just have statistical uncertainty. But in the observational study, we have the three type of components, right? Like statistical uncertainty, misspecification bias, and identification bias. And even if you're able to take care of the statistical uncertainty, which I think was one of the questions, even if you construct the right confidence intervals, et cetera, you don't know if the difference between the RCT estimate and the observational estimate is because the observational estimate, suffers from a lack of identification, right? So that's one problem. And then the second problem I see with this is that bad estimators can get lucky, right? Like if you have one estimator that's bad, maybe it has a different probability limit, and then these two biases happen to cancel out, then that's problematic. And of course, the question that was brought up, which is, there is self-selection of participants to the RCT and to the observational study, and what does that imply? Do we have different target causal parameters? Are those differences due to unobserved variables? So there is a lot of questions there. In terms of large sample properties, I think Luke also mentioned this. This is actually the main reason why approaches like the doubly robust plus machine learning estimation approach has been proposed, because this kind of approach can be shown to satisfy these properties. First, it behaves like sample mean in large samples. So if you have a lot of data, this is like an empirical average, so that's nice. The remainder term from that sort of approximation happens to be the product of two errors, the error in the regression of the propensity score and the error in the regression of the outcome. And if these two are small, well, then the product is likely to be smaller compared to either one. So this is a very nice property, and this actually can be seen as something that improves not only large sample performance, but finite sample performance as well. And the ML part comes precisely because that product of two errors that shows up in doubly robust estimators can be made small with machine learning. So these are the sort of the reasons why this approach is recommended. There is asymptotic theory also for many other methods. Some of the matching methods that were used in simulation studies also have nice asymptotic approximations, are efficient, et cetera. However, these large sample properties have a problem, which is they are useful only if they provide useful approximations that can be used in finite samples. Otherwise, they're really not good. And it's hard to know once you have a data set, once you have a given problem that you have to solve, it's hard to know if the approximation is good. So this is the reason why people maybe sometimes try to maybe not base so much their estimator selection and base it on large sample properties. And so I want to finish with sort of saying like the goal of sort of finding one estimator that works sort of best for all situations. I think it would be great if we could do that, but I think that's generally impossible. I tend to believe that these doubly robust plus machine learning estimators perform best in most cases, but there can be cases and sample sizes in which many of the other methods could actually perform better. And so I think there have been a few methods, and this is part of something I'm working on with some collaborators. But there are sort of new methods to start thinking about. Okay, how do we do estimator selection? And I'm just here providing a very quick description of how that could work, for example. And one way in which that could work is, let's say we define a model, statistical model P, and this model P can be constrained in any way you want. For example, you can say what are the number of variables that you have, binary, categorical, continuous, outcome type, etc. You can define some kind of a maximum amount of confounding that you'll allow in this statistical model. Complexity in the outcome covariate relationships, for example, as measured by the variation norm, and a fixed sample size, right? And so once you have this statistical model, you can start solving problems like this minimax type of estimation problem. So if you have a class of estimators T, which let's say include all the matching estimators, all the inverse probability weighted estimators, et cetera, that Luke mentioned, we can start trying to think, okay, so for every one of those estimation approaches, And for every sort of probability distribution in the model, I can compute sort of this MSE, basically the mean square error. And I'm going to take the worst case scenario, the probability distribution in the model that gives me the worst MSE, and then take the estimator that makes that worst case scenario not as bad, right? This is actually something that can be done in some cases numerically, and it would approaches like this. And as I said, there are many approaches that work with this idea. Approaches like this can actually be maybe solved numerically and can provide a more sort of principled solution to this problem of estimator selection. But anyway, this is all very recent, and I don't think it's ready for use in practice. And with that, I'll stop. Thank you.
Thank you, Iván. That was a really interesting discussion. Luke, I encourage you to, I guess, comment on some questions raised in the discussion, and then maybe we can go through some of these questions. I will say any of the questions that we don't get to, obviously, because there is a lot of them, will be forwarded to Luke after the talk, so you can feel free to start your discussion with him offline. But yeah, Luke, please take it over.
Yeah, Iván, thanks for those comments. Those are great. I don't have any real responses. I mean, I don't have any. There were new issues raised that I feel like I really need to respond to. So why don't I work my way through some of the Q&A here? So the first,
sure.
and I'm going to go in. Do you want me
Ivan,
to read
if
them,
you
or
could,
do you want?
You can go in the way you want. So yeah, perfect. I was just going to ask to stop sharing screen. Yeah, great. Go ahead.
So I'll go in the order by which they're asked. So I'll go back in time to the first question and work my way toward the more recent questions. Are the theoretical, so this is Leon Di Stefano, are the theoretical optimality results for DML mostly asymptotic? I think Iván sort of answered that. I think just yes, by and large, yes. Then the next one is, why is AIPW considered treatment only as opposed to modeling both outcome and treatment? Okay, this is a confusion between the way Stata labels things and the way things. So AIPW is often refers to augmented IPW, which is a doubly robust method. In Stata, however, AIPW means they're using stabilized weights. You know, oftentimes the weights are, instead of 1 over the propensity score, it's the propensity score, you know, the stabilized version of the weights. So when I use the AIPW, I follow the Stata convention, and that just means stabilized IPW weights, not an augmented inverse propensity score weighter that would be considered doubly robust. So that's just a matter of, I think, nomenclatures. How do you get the standard errors for the bias estimate, since the covariance between the experimental and observational methods is presumably non-zero, bootstrapping the difference? There are a couple of different ways out there that you can do this. There's actually, for standardized bias, there's a closed form estimate of the confidence interval. There's a package in R, and I did it that way. There is a way to bootstrap it. I've tried that in other settings, and it didn't make much difference. So there's a formula for a confidence interval on a standardized difference, and I use that formula. And then the next question by the same person: what covariates are you including when you implement the observational methods? Do you have a rich set of covariates that people say we need for matching to work? So this is an interesting question when you say a rich set of covariates. The richness of the covariates almost always depends on the original study design and who decide what covariates they decided to collect. And that is essentially what we are constrained by here. The reflux investigators, for example, I'm not a clinical expert to know that they captured everything. They have baseline measures of the outcome, which I think are particularly often useful. They have a fairly rich set. I think the RHC data definitely has a very rich set of covariates. Again, I didn't have any control over that. I used all the ones that were generally included in those data sets. There are quite a few. I off the top of my head, I don't remember exactly how many there are, but in terms of what I do know, in the RAC data, the data is much more, so in clinical studies, data tends to be either what we call a registry data or claims data. Claims data is collected usually at a higher level and doesn't include bedside measures of physiology. The RAC data includes a number of measures of bedside measures of physiology, like mean arterial pressure, blood pressure, bilirubin, things like that. So in that sense, I would say the RHC data is much richer than quite a few of the other claimed data sets that get used for medical studies. The next one is, as per John King's comment recently, we should stop using PSM. Should we start using Mahal notice distance? Any comments? So I think they mean Gary King. Should we stop? I mean, I don't want to make huge generalizations. If propensity score matching is easiest, the only thing you can really do, sure, use it. In general, I do think, yes, in terms of matching, there are much more sophisticated methods out there that will make your life easier and probably balance things a lot faster than most PSM implementations. So I would generally agree with that. What is the size of the estimation error around the vertical line? I'd have to go back to the original paper if you want to follow up with the original paper. I don't know that off the top of my, without the paper here, sorry, I can't answer that. What was the basic model specifications? Was this connected to the common multiplicative regression models using EQ5D value set estimation? Or were they more common regression treatment estimation specifications related to some other quantities? If related to multiplicative models, how are the results related to the specific model specification? So the basic model specifications, I actually use pretty vanilla ones in terms of just linear. I didn't include any interactions. It wasn't clear to me. I talked to some clinicians and they weren't, this is where I do think sometimes machine learning is quite helpful when I go and I talk to clinicians and I think, so what do you think of the key interactions here? And they're like, good question. We've got 20 variables. There's the number of possible interactions is quite large. So the specifications there, we didn't include anything multiplicative other than what would have been generated through the machine learning fits. If I'm a Stator user, which command will you recommend? That's a good question. I wouldn't recommend any of the, in general, it looked to me like I would definitely use the TE-effects commands with both IPW and what they call APW, but then also check the regression, add the regression adjustment on top of that and hope for concordance across all. If you get concordance across 2 or 3 of those methods, you're probably safe in terms of being a Stator user. But I would stay away from the NN and the PS match commands and stick with the variations on the regression adjustment with and without on the IPW and the IPW command. I missed it. How did you get the true effect? In Reflux, we have the data and we have the RCT data. In the RHC data, there's a couple of published papers that did similar trials and they're just published, but we don't have the data there. So that's a much more informal setup. In the propensity score matching, we actually included all of them. Right. The other advice would be to include those that are imbalanced. Like there's a rule of thumb. I do any covariate that's got a standardized difference of larger than 0.15, you might put in the outcome model. But here we put them all in. Okay, push back on this. It doesn't matter so much if they're similar on observables. The differences between observational experimental methods must be due to differences on unobservables. And we can't tell if this difference in unobservables between treated and untreated NRS or difference in unobservables between RCT and NRS. Yes, that's true. Right there, we have 2 forms of unobservables here. That's always a risk. To me, this is more of a risk of when you fail to recover the experimental benchmark, right? If every method fails to recover an experimental benchmark, then right, there are obviously 2 sources of unobservables that might be driving that. When I successfully replicate an experimental benchmark across many different methods, that suggests to me that the unobservables are not problematic in these settings. Okay.
Yeah, so maybe we should also wrap up soon. So feel free to pick out your favorite.
Okay.
Yeah.
This is one that I think is actually quite relevant. What do you recommend for projects with limited computational capacity? For our example, our chemical projects are often very large data sets, and using the ML methods or even some PSM methods will overwhelm the data platforms that we must use. Yes. So the fastest thing I have seen lately is some of the newer balancing weight methods, approximate balancing weight methods. Avi Feller and Eli Ben Michael, one of his students who's now at Harvard, they have an implementation of balancing weights that I have found to be very, very fast. With data sets of over 1 million observations, we can get really great balance in less than 5 minutes. And then on top of that, you could do some sort of more vanilla regression adjustment. That strikes me as an approach that should be pretty feasible in any computational setting. So that would be my recommendation there. Most matching methods are not great, I think, when computational capacity is limited, other than more generic ones. So there are 100 people probably just groaned at my response there, but from my experience, some forms of balancing weights are definitely the fastest in terms of doing treatment focused, and then on top of that, some sort of more vanilla regression adjustment should get around that. Someone said I should talk a bit about untestable assumptions. And someone else respond that yes, there are different methods of sensitivity analysis. Yeah, I agree. Sensitivity analysis, different study designs. I think one way I really like to understand observed bias is if I have an instrument, use an instrument, conduct an observational study that targets the ATE, use a regression discontinuity. I think they're trying to target the same causal question with different study designs that make different assumptions about the unobservables is probably one of the most effective way. I'm not going to claim responsibility for that idea because that's an idea that Paul Rosenbaum has talked about for many years. But I think in particular, that's probably sensitivity analysis is fine, but sensitivity analysis is and I don't do it, but it's still a thought experiment. Ideally, let's find, I think it's worth finding different study designs that make different assumptions about the unobservables and seeing what sort of congruence you get across different study designs on the same causal question. Not to shout too much at the economists, but like if you read the literature on college education, yeah, it's based on instruments. A lot of people hate instruments, but they've used a lot of different instruments that have clearly different sorts of biases and they get the same result. That to me is a good sign. So I think I'll keep it there in terms of what's left. Feel free to, I'm very easy to find on the web. If you want to track me down and email with questions, I will answer them at some other period later this week.
All right, perfect. So in that case, right. So thanks, Luke and Iván. Just 1 second. There we go. For the wonderful talks and thought-provoking discussions, and also for answering so many questions. And thank you, the audience, for asking so many questions. Actually, it's been very engaging. So next week, actually, we have one of our own. So Dominic Rothenhäusler from Stanford will present his work on calibrated inference, statistical inference that accounts for both sampling uncertainty and distributional uncertainty. So we hope to see you all there. Thanks, and have a great day.